Okay, so I promised you that we were going to get a ton of value out of resonance structures and out of curved arrow notation with resonance structures. And so here's a big deliverable. I hinted at this in a previous video, but we're going to see that when we look at resonance structures, if we're careful with our formal charges and if we're careful with our line bond structures, we're going to have real obvious indicators of what is stable and what is not. And then we're going to assess the relative importance of the resonance structures, okay? So recall that when we first talked about resonance, we found that resonance structures are just contributors to a resonance hybrid, and that the actual structure is not any of the contributors, it's a blend of all of them, right? Now, one thing we typically oversimplify in the beginning is we start to think it's sort of like a half and half blend, okay? But it's only a half and half blend if both of the contributors are equally stable. All right, let me say that again. It's only a half and half blend, 50-50, if the two contributors are equally stable. But if they're not equally stable, then the one that is the most stable is going to be the greatest contributor. Okay, I hinted at this in a previous video, but we're going to probe it now. So we're going to look at some rules that are going to help us appreciate what is the greatest contributor to a resonance hybrid and what that even means. Okay, so let's look at rule number one. Rule number one is the most significant resonance forms have the greatest number of filled octets. Okay, so if we had a carbocation that was next, if we had a carbocation, let me go here with my drawing. If we had a carbocation that was next to a lone pair of electrons, right? This was one of our 5 types of resonance contributors. Then we would say that, yeah, these electrons are going to come over here, right? Just like we see here, okay? They're going to come here. Now, if they do, this is what we're going to get. So the most significant resonance forms are going to have the greatest number of filled octets. Can you see that this does not have a filled octet, but this one does? If that's true, then this is the major contributor, and this is the minor contributor, okay? Now, in this structure, as we see, all atoms have an octet, so it's the major resonance contributor. Let me say another minor thing about this, and I'm going to say it about you as we go along. That means that the real resonance hybrid looks like this, right? And it's got a lone pair here, okay? Now look, when we have, can you see that we have a partial charge here and a partial charge here? Because in this structure, it's neutral, the oxygen's neutral. In this one, it's oxygen, it's a cation, right? So the real thing is a mix between the two. Neutral plus plus is partial positive. Same thing here. Partial positive, neutral, so it's going to be partial that's a positive. I'm saying this wrong. It's 9 o'clock at night. It's my problem. So it's a carbocation, but it's neutral over here. So the real thing is going to be a mix between them. Now the next question is, which of these positive charges is bigger? Which of them is bigger, right? We usually just say partial. We rarely quantify that, but you can quantify that here. If this is the major contributor, then this is going to be the one that has the greater positive charge. So this partial positive is actually greater than that one. This is smaller. Okay, we're going to do that with a couple other examples. All right, we'll do that each time. Now, rule number 2 is that the structure with the fewer formal charges is more significant. Okay, so can you see here that I have no formal charges here, right? But I have a lone pair of electrons next to that are allylic, right? Remember we talked about that in the last video? So if these are allylic, these electrons can come down and these electrons are going to come up, right? But when we do that, this nitrogen, which was neutral, is now going to have a positive charge on it, right? It's a partial in the real thing, but in this structure, it's shown as a formal charge of +1. And this nitrogen, which was neutral and now gets more than its fair share of electrons, is going to have a -1. So this is going to be less of a contributor than the largest contributor, okay? But when we have a structure that does not have a filled octet, this is minor. This is less. this is minor yet, or less yet. Man, my vocabulary is just gone tonight. All right, so this is minor yet. So we're going to say that's a very minor contributor. This is the greatest contributor, and this is the next greatest contributor. Okay? Let's look at another example. Let's look at a compound that has a lone pair of electrons that are allylic, again, right, to a double bond. So if this compound has an overall formal charge, then we focus only on resonance forms that show the delocalization of that charge. So we start out with a negative charge here. We're not going to get like a negative charge and a negative charge. We're not going to get two negatives and a plus. So this is irrelevant. Okay? I mean, of course, such a structure exists, but it's so low in energy that it's essentially negligible. All right? So these electrons are going to come down here because they're allylic, right? Those electrons are going to come up here, and we're going to get this shared. Now, going back to the question I was asking earlier, I think I was using a green marker. Which of these is the more stable contributor? Which is more stable? Well, oxygen's more electronegative, right? And so this is going to be the more stable one. And so if we're going to draw the real thing, we're going to see that, right? And the carbon here, this is a little bit thick, okay? We're going to have a double bond here, partial double bond, right? Partial double bond there, right? And we're going to have a partial minus here and a partial minus here. But which partial minus is greater? Aha, that is greater because it's the electronegative oxygen is going to have more than the not so electronegative carbon, okay? So this partial negative is going to be greater, right? So they're not shared evenly. You can see that. That's what this example is about, okay? Now, rule number 3 is that a structure with a negative charge on the more electronegative atom will be more significant, which is what I just alluded to, all right? So, and that's what we just said. I got a little ahead of myself there. You can see that this is going to be the major contributor, which is what I was saying on the previous slide, and this will be the minor, okay? But let's look at another example. The more electronegative of these two is oxygen, right? And so since that's the less electronegative of the two, it's going to be more likely to have the plus charge on it. All right, so you have the plus charge here and a plus and a plus charge over here. But this is going to be the major contributor because the more electronegative element is not got a positive charge on it. All right, that's going to take some practice. We'll have some examples we'll practice with. All right, and that is those are the only 3 rules that we're going to have to consider when we're looking at the quality of resonance structures for now. We do have some more coming up in the future.